Hey ChemStars, it's Ms. Macaulay bringing you your next Chapter 21 nuclear flipped video. We're on the bottom of page, or the top of page 10, 21.4.1, Fission and Fusion of Atomic Nuclei. So here's our I can statements. I can compare the process of fission and fusion, and I can compare the energy released in a chemical reaction to the amount of energy released in a nuclear reaction. Our key vocab words are fission, fusion, and we'll look at mass defect. So fission and fusion right now. So let's start with nuclear fission. In 1936, Lisa Meitner was trying to make a larger uranium nucleus by bombarding it with neutrons. So this is another form of the artificial transmutation. Please make a note. So whenever we have two reactions, that's called artificial transmutation. Instead, she ended up breaking the uranium into smaller parts and releasing energy. She discovered fission. So here's an example of the reaction she was trying to do. She took a uranium-235 radioisotope, accelerated a neutron towards it, and then it broke up into smaller pieces, and she got a krypton-91, a barium-142, and 3 neutrons plus energy. So here's a picture of the reaction here. We can see we added the 1 neutron. So we can see there are 2 reactants. It made a new very unstable uranium-238 radioisotope, and then that broke apart into 2 different smaller isotopes, 3 neutrons, and plus lots of energy. So let's predict what will happen when the released neutrons strike other uranium-235 nuclei. So you really can't ever have just one atom. You're going to have a sample that has hundreds and hundreds and hundreds of atoms in it. And if we put in 1 neutron, we get 3 neutrons out. What are those 3 neutrons going to do? Well, each one's going to strike another reaction. So what's going to happen? We are going to get a nuclear chain reaction. So once this process starts, it's going to keep going and pick up speed. So that brings us to Enrico Fermi. So at the bottom of page 10, let's look at what Enrico Fermi discovered. Okay, so Enrico Fermi, he discovered the chain reaction. Some of the neutrons produced react with other fissionable atoms, that means atoms that can undergo fission, producing more neutrons, which react with still more fissionable material. So here we can see that chain reaction starting. So we start with 1 neutron. After 1 collision, we get 3 neutrons. After the next collision, we get 3, 6, 9 neutrons. So we went from 1 to 3 to 9. So what kind of growth or decay would that look like? That would be exponential growth. So we're going to have exponential growth there. Okay, flip to your next page, please. So let's look at 2 types of fissionable reactions. So our key I can statements for this section, we've got I can consider the consequences. Oops, let's try that again. So I can consider the consequences and alternatives of using nuclear energy. And I can explain the differences between a nuclear weapon versus nuclear power. And I want you to think back to the Fallout video we watched in class. And we also will talk about renewable versus non-renewable energy. Okay, so atomic bombs. Uncontrolled. Once you start, you can't stop. If you watch popular TV, they'll talk about critical mass. So once you have critical mass, the chain reaction is going to keep going, keep feeding, and cause a really big release of energy. However, on nuclear reactors, we don't want to have uncontrolled. We have a very controlled reaction. The process can stop and can be slowed down and modulated once it started. So how do we control those nuclear reactions? One way is called neutron moderation. So through neutron moderation, the scientists slow the neutrons down so the reactor fuel captures them to continue. They use things like water and graphite, and that gets rid of a lot of those excess neutrons that are produced. Another type is called neutron absorption. It decreases the total number of those neutrons, and those are things made out of cadmium. So the moderation slows them down, and the absorption kind of sucks them up and takes them out of the reaction. So you've got a diagram here where we have some of the fuel rods. So we have fuel rods and then the control rods. The control rods are there, and they're part of the moderation and absorption. The nuclear reaction generates heat and steam, which then turns the turbine. and then gives some electrical output. So when you look at this, it looks like, oh, it's pretty clean energy. It's taking in cold water, but one important thing you need to look at is that it puts out hot water. Nuclear plants aren't required to cool the water back to the intake temperature, and that can have lots of ecological consequences. So that hot water can have lots of ecological consequences. So certain species of fish might not be able to live in the same body of water anymore. It can cause changes in the algae levels. So it has lots of different repercussions if that water is returned hot. Let's see some of the other problems with nuclear power plants. One of the big ones you probably think of is nuclear waste. What do we do with all of those radioactive, all those hot radioactive sources? So the spent fuel rods are made up of fissionable isotopes, usually uranium-235 or uranium-239. Once they've been used up all they can be at the nuclear power plant, they take 300 and they bundle them together, and they have to get rid of them somehow. They need to be replaced, but where do we put the old ones? Typically, the rods are still hot. They produce heat for years after their removal from the core, and they have to be stored somewhere. They can stay up to 10 years in a holding tank inside the plant, and then they're taken to an off-site storage facility like Yucca Mountain. But let's say you have a nuclear power plant up near Cleveland, and you need to transport it to Yucca Mountain in the American Southwest. How does it get there? So they can be transported on trains. They can be transported by trucks. So all over the country, we have nuclear material just out in public. Okay, and let's go to the last page of our notes. So now we've talked about fission. Let's talk about fusion. So nuclear fusion is what actually is happening in the core of stars. So if you've taken astronomy, you'll know all about this. So fusion occurs when nuclei combine to produce a nucleus of greater mass. So for example, in the sun, hydrogen nuclei fuse to make helium nuclei. Let's look at this picture. So here we have 4 hydrogen nuclei, and we get 1 helium nuclei plus 2 positrons and energy in the form of heat and light. So what other particles are produced by this reaction? Right here, we see our answer. You get 2 positrons, plus you get lots of energy. It could be gamma radiation. It could be visible light. Also, we get heat from the sun. Fusion occurs in the sun and in atomic bombs. You cannot have a nuclear reactor with fusion because you need at least 40 million degrees Celsius in order for fusion to occur. So fusion is a lot more desirable when it comes to nuclear energy. You get a lot more energy out, and you don't have to worry about those radioactive byproducts, but we can't get those kinds of sustained temperatures inside nuclear reactors. Atomic bombs, on the other hand, they start with a fission reaction to get temperatures that high, and then they go into fusion. That's when you hear them talk about the H-bomb and things like that. So what scientists and physicists are always looking for is cold fusion. Could we make nuclear fusion happen at like relatively normal Earth temperatures? The goal is to get that reaction going. That way they can get more energy and not have to deal with all the radioactive wastes. Only a clean energy source with helium as a byproduct. And you might have heard there is currently a helium shortage. So if we could get clean energy that also produces helium as the only waste product, that would be really good. Okay, so our next thing is we're going to look at a graph. So we're going to build this graph together. So on the x-axis, we have atomic number. We have atomic number 1, that is hydrogen. Atomic number 26, that is iron. And then we have atomic number 92, which is uranium. So up on the y-axis, I want you to label that mass per nucleon. So that is mass per nucleon. Nucleon's a new vocab word. It's just a fancy way to say either protons or neutrons. So here's the graph we're going to draw. So you're going down towards iron, and then once you hit iron, you kind of level out and then start coming up again by uranium. So here's our point of inflection, our POI. So let me explain a little bit to you before we get into this. So on this side of the graph, we have fusion. That means elements from hydrogen to iron can undergo nuclear fusion. Elements between iron and uranium, they will undergo fission. So that's something we've observed, but why is that true? So if you go back to your reading, there's something called the mass defect. we've simplified some things before, and we've told you that 1 proton equals 1 AMU, and all protons are the same. That actually is oversimplifying it. In reality, hydrogen protons have more mass than any other proton. It's not a lot more, it's not like 2 or anything, but they have incrementally more mass. And so what happens is when those hydrogen protons fuse together to form helium, some of that mass is converted into energy. So that's called the mass defect, and we actually have an equation that describes that. Albert Einstein gave us that equation, which is E equals mc squared. So energy is equal to mass times the speed of light squared. So some of that mass is being converted into pure energy. So that mass defect, mass is converted into energy. And this explains why you can get more energy out of fusion. Look at the slope of this line. So it has a greater slope. There's a greater mass defect here. A lot more energy can be freed up. When you look at the fission, the slope really kind of tapers off, but starts to go up when we get back towards uranium. So you'll get more energy from uranium fission than you would from something over here. And you'll get the most energy from hydrogen fusion. That brings us to this question right here. What about at iron? At iron, actually, it can't undergo fusion. It can't undergo fission. Iron won't do anything. It's at this kind of bottom of the energy well. So iron will not fuse. It will not undergo fission. It is stuck there. We'll go over this again in class too. It's a little bit more complicated than some of the other topics we've tackled. So how do nuclei make energy? So how do they, quote unquote, make energy? They convert mass to energy. The equation, like Einstein gave us, is E equals mc squared. So where does fission occur? Fission occurs past iron through uranium. So that's atomic numbers 27 to 92. Where does fusion occur? It occurs from hydrogen up to iron. So that's atomic numbers 1 through 25. And poor iron is stuck in the middle and can't undergo either process. So what kind of nuclear energy would iron give off? None. It will not give off any nuclear energy. And this is the reason stars will fuse up to iron and then they will die. Maybe with a supernova or maybe just slowly going out. So looking at this graph, why does fusion give off more energy than fission? Look at the slope. So if you look at that slope of the graph, that explains everything. The change in mass is greater up here. That means you can convert more of that mass to more of the energy. So thanks for listening to all of our Chapter 21 notes. Make sure you come to class with questions. Bye, guys.